Hi everyone. The goal of this lecture is to develop concepts, formalism and techniques for the quantum dynamics of field. We are all familiar with the Maxwell's equation that describes the electric and magnetic fields, right? So these are all classical. Since we all live in a world that requires a quantum description, we should also treat the electric and magnetic field using quantum language. Once you treat electric and magnetic field quantum mechanically, you get the concept of photons. And the photon is now the fundamental particle that mediates the electromagnetic interactions. So you get a completely different picture from what you get classically. So if you treat electric and magnetic field quantum mechanically, then you get photon. So among the four fundamental forces of nature, three are described by quantum field theory. Okay, the strong, weak and electromagnetic force. These three are described by quantum field theory completely. At the moment, quantum field theory does not offer a complete description of quantum gravity. But still you can use the quantum field theory techniques to understand certain questions of quantum gravity. Nowadays, quantum field theory has become a universal language for theoretical physics. So if you are really serious and want to take up research in theoretical physics, then you need to master quantum field theory. So in the upcoming classes, we will attempt to develop the fundamental concepts of quantum field theory. So quantum field theory or QFT is essentially quantum mechanics, okay, but we have to deal with infinite number of degrees of freedom. Infinite number of degrees of freedom. So in quantum mechanics, you always consider finite number of degree of freedom. So this infinite number of degrees of freedom makes some differences. So these actually make differences in the concept also, right? And therefore, quantum field theory actually deals with some formalisms. Formalisms in the sense some tricks that are applied, okay? And these formalisms are designed to solve some concrete physical problems or questions. Therefore, you have to learn from experiences and then develop intuitions. Therefore, the first discussion in this course will be, why do you need quantum field theory? To answer this question, we have to start from the basics of classical field theories and we have to discuss its disadvantages. So first we will discuss classical field theory. CFT or the classical field theory is based on an important concept of the principle of locality. Okay, principle of locality. So the example for principle of locality are the Newtonian mechanics and the Coulomb interaction between the charged particles. Okay, so for example, consider the Coulomb interaction between the charged particle. You have a positive charge and you have a negative charge and they are attracted towards each other. So this is a Coulomb interaction between the charged particles. Okay, so all the points in this space participate in the physical process, even if it is attraction or repulsion between two positive charges or repulsion between two negative charges. All the points in space participate in a physical process. All the points in space participate in a physical process. And the effects propagate from a point to the neighboring points. And this principle of locality leads to the definition of field. The main idea of the field is that we associate each point in space with a dynamical variable. Okay, so what is a field? The main idea of the field is that we associate each point in space with a dynamical variable, and this dynamical variable is called the field. Okay, so example for the field. Okay, example for the field, I can say electric field. So here I denote x and y. X and y are labels. Okay, so electric field and magnetic field are the most familiar example for fields. And using this electric and magnetic field, you can describe the Maxwell's equation. The Maxwell's equation are given by divergence of the electric field is equal to 4 pi rho, divergence of magnetic field is 0, partial derivative of the magnetic field with respect to time is minus del cross E, and del cross B is equal to 4 pi times the current density plus partial derivative of the electric field with respect to time. Okay, so the Maxwell's equations are best examples of principle of locality, because here you can see that the electric and magnetic field are defined at the same point in this equation. The effect propagate from point to point. Okay, if you take del cross B, if it is Bx, then automatically on the other you have Jx and Ex everywhere. Okay, so these are all local equations. The Maxwell equations are local equations. So what do you mean by local equations? The equations that contain electric and magnetic field at the same point with finite number of derivatives are called local equation. The equations that contain electric and magnetic field at the same point with finite number of derivatives are called local equations. The effect will propagate from point to point. For example, we cannot have By on one side and Ex or Jx on the other side. If it is x, then all the quantities has to be defined in the point x. If it's y, then all the quantities must be defined in y. So you cannot use both x and y. Okay, because these are local equation. Local equations are equations that contain the electric field and magnetic field at the same point with finite number of derivatives. So this is not possible. Okay, and the effect will propagate from one point to another point. And how does this effect propagate? These derivatives actually will help to propagate as it relates the point, one point to the neighboring point. Okay, so the propagation happens through the derivatives because the derivatives relate one point to the other neighboring point. And the second example for field is the Einstein's gravity. In Einstein's gravity, the dynamical variable are the space-time metric. Okay, the dynamic variable is the space-time metric, which is given by g mu nu of x comma t. Okay, so here you can see there are two indices, which means that it is a tensor field. And the effect of gravity is propagated through the space time. Okay, now let's briefly discuss the type of fields. What are the different types of fields? First one is the scalar field. Scalar field is denoted by phi, and scalar quantities are the quantities at a given point will have only a single value. For example, temperature. So example for scalar field will be the temperature field. It has only, at a given point will have only a single value. And the second type is the vector field. Okay, so we can use a 4-vector notation, something like a mu of x nu. Okay, so here space time is combined together in nu. Okay, so at each point there will be a vector. For example, the examples of vector field are electric field and magnetic field. And then third type is the tensor field, which will have more than one indices, right? More than one index. And the example is the fundamental metric tensor G mu nu of x lambda. So this is an example for tensor field. And you have one more category of fields, which for the time being is not required, but we'll see it later while learning the quantum electrodynamics. And this type of fields are known as the spinor fields. And it has a form psi alpha of x comma t. Okay. So throughout this course, we will follow a single convention. Okay, so our convention will be that the indices mu and nu will always run from 1 to 3, which means it has both time and spatial coordinates. For example, x mu will be the time part and the spatial part. Okay, and the spatial part is always indicated by I or j or k. Okay, etc. And the partial derivatives is defined. It also has both time and space, and any vector a mu can be described as its time component and spatial component. And throughout this course we will also follow the natural units. Okay, this is just for the notational conveniences. We will follow the natural unit. The speed of light c will be taken as 1, and the Planck constant and the reduced Planck constant is taken as 1. So before going to the quantum field theory, first we will start with classical mechanics and then slowly build our intuition to classical field theory and then quantum mechanics and then to quantum field theory. So that will be the approach. So we have to recall the action principle in classical mechanics. Okay, in classical mechanics we have the action principle. So we introduce the action S as the time integral of the Lagrangian, right? The Lagrangian is a function of position, velocity and time. Okay, and the action is defined as the time integral of Lagrangian. And we can also define a canonical momentum P, which is given by partial derivative of the Lagrangian with respect to x dot. We can define the Hamiltonian, which is related to the Lagrangian by a Legendre transformation. So the Hamiltonian H is given by Px dot minus L. And equation of motion can be obtained by extremizing the action, that is delta S is equal to 0. So by extremizing the action, you can always find the equation of motion. Now for classical field theory, we have to invoke the principle of locality. Okay. So now this is classical mechanics. From classical mechanics, we move on to classical field theory. So when we move on to classical field theory, you have to invoke the principle of locality. And once you invoke or consider this principle of locality, the Lagrangian will be significantly constrained. Okay, so the Lagrangian will be constrained and it will be of the form the volume integral of a Lagrangian density. Okay, so since we consider the principle of locality, the Lagrangian density will be a function of the fields, then time derivative of the fields and the spatial derivative of the fields. Here A is a label and phi A represents a group of fields. It can be phi 1, phi 2, phi 3, etc. Okay. So if you invoke the principle of locality, then the Lagrangian will be severely constrained, and the Lagrangian is now the volume integral of Lagrangian density, and the Lagrangian density is a function of fields, time derivative of field and spatial derivative of the fields. Okay, and we can also see that this Lagrangian is still local. This Lagrangian density only depends on the value of the field and its derivative at a single point. Okay, so this is still local. Now why must Lagrangian have this form? Okay, so why it is not allowing another terms or another form? For example, why don't I write the Lagrangian as something, some equation containing the term d cube x d cube y, phi of x comma t, phi of y comma t. Okay, if Lagrangian has this term, then equation of motion will not be local, because here you see you have two different points. Okay, so equation of motion will involve the behavior of the field at one point, which will be influenced by point which is far away. That is, if you give away locality, then your Lagrangian will be complicated. Okay, so we always consider principle of locality, because if I don't consider principle of locality, then Lagrangian will have this form. Okay, I don't want this form because this is arbitrarily complicated. So I don't want this term, cross terms, to come. Therefore, I always prefer principle of locality. Okay, because if I have all this term, then the integrals will be more complicated, and you can also have more integrals as you want. So I can keep on adding such terms, okay, which will complicate the Lagrangian. So I don't want such complication. Therefore, I always consider principle of locality. If you want to consider the principle of locality, then the behavior at one point will or should not be influenced by another point. It should always be defined at the same point. Therefore, I will not consider cross terms and I will only allow locality. Okay, and also one more thing to see is that the Lagrangian will allow only first derivative in time. Okay, I will allow only first derivative in time. If second derivative in time is allowed in the action or in the Lagrangian, then the equation of motion will involve more than two derivatives, right? So in real life, all the experiment is determined by the initial condition. So initial conditions in the sense the location and the velocity. Location x and the velocity x dot. Okay, so these are the initial conditions in the real life. If I have more than two derivatives, then it will be the acceleration, right? Then I have to modify the initial condition to include the acceleration also. Okay, so I have to specify more general initial condition, so which I don't want to complicate. Therefore, we allow only first derivative in time. Okay, if second derivative in time is allowed, then the equation of motion will involve more than two derivative, because we have to again take one more derivative there. So in principle, you can allow arbitrary number of derivatives in spatial direction. So this is in time. Okay, so first derivative is allowed only in time, but in space you can allow arbitrary number of derivatives. But for simplicity, most of the time we stick to quantum field theory in special relativity. Okay, which means it will be Lorentz invariant. So in Lorentz invariant theory, space and time can transform each other. So if I write more than one derivative in space, then it will also reflect in time. Okay, so if you have only single derivative in time, then you have only single derivative in spatial direction. Therefore, I always prefer single derivative in both in space and time, so that it will be Lorentz invariant. In non-relativistic system, you can have higher number of spatial derivatives. Okay, so we always deal with the relativistic system, therefore I prefer only single derivative. Now, similar to classical mechanics, we can define canonical momentum, Hamiltonian, etc. in classical field theory also. So here we have canonical momentum, Hamiltonian. These are all for classical mechanics. So similarly, in quantum field theory also, I can define the momentum, canonical momentum, Hamiltonian density. So here when it comes to classical field theory, it is not just Hamiltonian, it's Hamiltonian density. Okay, it's not just Lagrangian, it's Lagrangian density, right? So similarly, in classical field theory, I am going to introduce the canonical momentum density, canonical momentum density, which is given by capital pi a of x comma t. Okay, it's defined as the partial derivative of the Lagrangian density with respect to phi dot a. This is a function of x and t. Okay, so phi dot means, what is phi dot here? Phi dot means the time derivative of the field phi a. That's it. Okay, so this is the canonical momentum density. Now once I get the canonical momentum density, I can define the Hamiltonian density. The Hamiltonian density H is defined as phi dot a pi a minus the Lagrangian density. Okay, and the Hamiltonian H is given by the integral of Hamiltonian density. Okay, so the the classical field theory is just like classical mechanics, but the thing is, you generalize it to infinite number of degrees of freedom. That is the only difference. In classical mechanics, you have a single particle as an entity, but here you have fields, right? Which means the action in classical field theory I can write as, now what is Lagrangian? D cube x Lagrangian density, right? So Lagrangian is now integral of d cube x Lagrangian density, and I can rewrite this as d4x. Now this contains both time and space integral. Okay, d4x. So I am combining dt and d cube x into d4x, and now I have Lagrangian density, which is a function of phi a and del mu phi a. So this is the action in classical field theory. Now to get the equation of motion, let's vary the action. Okay, to get the equation of motion, I have to extremize the action. And so how do you vary the action? Then I have to vary this equation, right? I have to vary this equation. Then integral d for x, then it's just a straightforward variation of the Lagrangian density with respect to the field plus variation of the Lagrangian density with respect to del mu phi a, right, multiplied by the variation in del mu phi a. Right? So here the variation in del mu phi a is equal to the derivative of variation in phi a. So you can interchange like this. Okay, this is possible. Now I have to rewrite this second term. I am going to rewrite this second term. So if I write a complete derivative of the Lagrangian density with respect to del mu phi a, then this will be equal to, okay, I have to expand. So first I have to take the derivative of this term, and then which is multiplied by second term plus derivative of the second term multiplied by the first term, right? Okay, so let's see. The complete derivative of this product of one variation and one derivative. So how do I expand it? I can write del mu, right? So first I'll take the derivative of the first term. So first term is this one, multiplied by the second term plus, now the first term as it is, and derivative of the second term, right? But here in this equation we have this form, right, which is this one. So I can define this term as the total derivative subtracted by this term, first term. Then I will get the second term. So I can rewrite this equation as is equal to the total derivative, right? The total derivative minus multiplied by delta phi a. Okay, so now I am going to substitute this in the equation of motion here. Okay, so delta S is equal to 0 means the quantity in this bracket must be 0. So what is there in the bracket? I'll list it out. The equation of motion, right? The equation of motion will be now partial derivative of 5a multiplied by del phi a, right? And now the second term I am going to replace it by this term. Okay, so equation of motion will be this plus minus multiplied by del phi a, right? Now here I can rewrite this equation of motion as, again I am going to rewrite. So I can take this delta phi a common from the first and the last term. Then I can write the entire thing multiplied by delta phi a, and the other terms I am just writing plus boundary terms, right? Now these boundary terms are not of much significance because we always choose the delta phi a such that the boundary term vanishes, okay? And therefore in classical field theory the equation of motion is given by equal to 0. So this is the equation of motion in classical field theory, okay? This is the general equation of motion for classical field theory. Now from now onwards we restrict to field theory that are translationally invariant and Lorentz invariant, okay? So translationally invariant means there is no special point in this theory. If you do an experiment in India, then it will not be different from when you do it in some other country in Europe or Africa. So that is known as the translationally invariant. And Lorentz invariant means it will preserve the laws of physics for different observers in uniform motion, okay? So for different observers who are in uniform motion, the laws of physics will be the same. So that's known as Lorentz invariant. So from now onwards we restrict to field theories that are translationally invariant and Lorentz invariant, okay? So examples for theories that obey the above invariances are, first one, Maxwell's theory, okay? So theories, examples for theories that obey these two invariances are, first one, Maxwell's theory. Maxwell's theory will obey both translational invariance and Lorentz invariance. And the dynamical variable in Maxwell's theory are the vector potential, okay, A mu of x, okay? From A mu of x the fields can be defined. So these are the vector potential. From the vector potential you can define the field F mu nu, okay? F mu nu is equal to del mu A nu minus del nu A mu, and the action is given by, action in electromagnetic theory is given by integral d for x, the Lagrangian density, right? So Lagrangian density is minus 1 by 4 f mu nu f mu nu. This is the action. If you vary this action, then you will get the equation of motion, which are the Maxwell's equation. Okay, that is Maxwell's equation in vacuum without any sources. And the second example that obeys translational and Lorentz symmetry is the Einstein's gravity. Einstein's gravity. So S is equal to, the action in Einstein's gravity is given by 1 by 16 pi g integral d4x. Now I have to write the Lagrangian density, which is root of minus g r. So what is r? We have already learned in general theory of relativity that r is the Ricci scalar. R is the Ricci scalar. Okay. Then the simplest field theories are known as the scalar field theory. Okay, so at each space-time point you will have a single value quantity, that is scalar field theory. Okay, so we consider a real valued scalar field, that is a real valued scalar field phi of x. Okay, so here phi of x is the dynamical variable and it is a real valued scalar field. And the simplest family of scalar action that you can write from this field, okay, I'll represent as S is equal to minus 1 by 2 del mu phi del mu phi, okay, minus v of phi. Now why there is a minus here, that's a question. So here we follow the special theory of relativity, which has a flat metric, which is a Minkowski matrix, which is given by minus 1. Okay, so this minus 1 is actually reflected here in the first term. Okay, and if you see this del mu and del mu, it's Lorentz invariant, that is the significance. Okay, and here it is based on the localities as well, and here the potential is phi dependent. Okay, and we always choose the translational symmetry and the Lorentz symmetry. Okay, so when you have translational symmetry, all the parameters in the potential v of phi must be a constant. Okay, that is, it should not depend on space time. So here we have selected phi as a real valued scalar function and it will not depend upon the space time, right? So the potential v must not depend on space time. So if you have some parameter dependent on space time, then different points will behave differently and they will not be translational invariant. Okay, now for this particular action I can define the momentum density. Okay, so the momentum density is given by dou L by dou phi dot. Okay, so what is Lagrangian density here? Lagrangian density is minus 1 by 2 del mu phi minus v of phi, right? Now this del mu phi is actually summed over. So when mu equal to 0, it is the time derivative, and I will get minus phi dot square, right? And for spatial part, sorry, phi dot square, and for the spatial part it will be gradient of phi square. Now if I take the derivative with respect to phi dot, then I will get 2 phi dot, and there is a half here, so half and 2 phi dot will get cancelled, and therefore pi of x will be equal to phi dot. Okay, and I can also write the Hamiltonian density pi phi dot minus Lagrangian density. So pi, I know it's already phi dot, and multiplied by phi dot will be phi dot square minus, now I have to write the Lagrangian density. Lagrangian density is minus 1 by 2 del mu phi minus v of phi, right? Now simplifying, I will get phi dot square by 2 plus half del phi square plus v of phi. Right? So this will be the Hamiltonian density. Once you get, then I can write the equation of motion. The equation of motion is partial derivative with respect to phi minus is equal to 0. Okay. Now substituting the Lagrangian densities, then I will get, see, partial derivative with respect to phi. Then here I have to write the Lagrangian density, which is minus 1 by 2 minus phi dot square plus gradient of phi square minus v of phi right. So this is the first term, and second term will be minus del mu of, again, derivative of the Lagrangian with respect to del mu phi. So if this is the Lagrangian density, then if I take derivative with respect to del mu phi, then the remaining thing will be minus del mu phi. Then I write minus del mu phi equal to 0. So here in the first term, the only phi dependent term is the v of phi. Therefore, it will be dou v by dou phi. Other terms are not dependent on phi directly. Okay, then the second term will be, so this will be minus because there is a minus here. So minus dou v by dou phi, and then minus of minus plus del mu will be del square. So del square phi equal to 0. So the equation of motion will be del square phi minus dou v by dou phi is equal to 0. This will be the equation of motion. So here del square is equal to partial derivative squared. Okay, so this will be in terms of the time derivative plus square of the gradient. And the simplest potential, okay, v of phi will be f phi. Okay, f phi. Here f is a constant. Okay, f is a constant and it does not depend on any position. Okay, because it has to follow the translational symmetry. Therefore, if we consider the simplest potential f phi, then the partial derivative of the potential with respect to the field phi will be a constant f, and the equation of motion will become, so you have to substitute this partial derivative here in the equation of motion, and I will get the equation of motion as f, right? So here f is the source for the field phi, okay, and it will act as an external force. If f is non-zero, then the field phi is also non-zero, so which means that the field phi is generated from the constant f. Okay, so the next simplest potential that v of phi can take will be of the form v of phi is equal to half m square phi square, half m square phi square. Then the derivative of the potential with respect to phi will be of the form m square phi. So if you substitute this m square phi in this equation of motion here, then I will get minus, right, m square phi will be equal to 0. So you can see that simplest field theory model that we can consider will give rise to the Klein-Gordon equation. So this is known as the Klein-Gordon equation. the Klein-Gordon equation. So you can consider more complicated field theories with v of phi to be higher polynomial or more complicated function with cos theta or sin theta, right? So half m square phi square is a special potential because it gives linear equation of motion. For any other potential, the equation of motion will be non-linear. So you can consider more complicated field theories with v of phi to be higher polynomials or more complicated functions involving trigonometries like cos theta or sin theta, etc. But always half m square phi square is special because it gives linear equation of motion. For any other potential, equation of motion will be non-linear and therefore it will get complicated. So here you can see in Klein-Gordon equation, both the terms are linear and therefore the equation of motion is also linear. Okay, so for the time being, today we'll stop here and we'll continue in the next class.